Hello, welcome you all for this new video on the new module beams and shaft. This is the part 1. This is the first video. Beam, it is a structural member which resists the transverse loading. Okay, in this beams and shaft we are deriving the stiffness matrix of the beam element and the shaft element. First we will consider beam element. For the beam element, first we need to find the shape functions. We already know that shape functions are used to find the displacement at any point within the element with the help of nodal displacements. Shape functions for the beams also called as the Hermite functions. It is a new word, Hermite functions. Shape functions for the beam element is called as the Hermite shape functions. Shape functions, I already told you, it is used to find the displacement at any point within the beam element with the help of nodal displacements. Okay, what are nodal displacements here? For the beam problem, for the beam element, when it is subjected to external loading, then in each node there is a vertical displacement as well as there is a slope. So in each node there are 2 degrees of freedom. One is vertical displacement and the other is slope or the rotation. So one element, this is a beam element, it has 2 nodes. In both nodes we have 2 degrees of freedom. So total there are 4 degrees of freedom, that is vertical displacement at node 1, that is V1, and slope, that is dou V by dou zeta. It is in terms of natural coordinates. Similarly, the nodal displacement at node 2, this is the node 2. Here the displacements, nodal displacements are vertical displacement V2 and dou V by dou zeta, that is the slope or the rotation in the node 2. So these are the 4 nodal displacements: vertical displacement V1, V2 and dou V by dou zeta at node 1 and node 2 are the slope or the rotations. These are the 4 nodal displacements. I already told you shape functions which are used to find the displacement at any point with the help of nodal coordinates. So this is the displacement at any point within the element. Here instead of n1, n2, n3, n4 we are using h1 shape functions for the beams, also called as the Hermite shape functions. As we have 4 nodal displacements for one element, we are taking h1, h2, h3, h4, and along with this nodal displacement, vertical displacement at node 1, rotation or the slope at node 1, and V2 and dou V by dou zeta are the nodal displacement at node 2. V2 is the vertical displacement at node 2 and dou V by dou zeta at, this is the slope at node 2. Here the displacement at any point, it is written, it can be calculated if we know the Hermite shape functions h1, h2, h3, h4. We are deriving the Hermite shape functions in this session. We already know what is the relation between natural coordinate and the global coordinates or the Cartesian coordinates. Zeta, it is in terms of natural coordinates, and x, it is the in terms of local or the global coordinates or the Cartesian coordinates. Zeta, it is already derived in the class. Zeta equal to 2 times of x minus x1 divided by x2 minus x1 minus 1, where x1 and x2 are the nodal points. Differentiating this equation, we have d zeta by dx, that is equal to 2 divided by x2 minus x1, it is nothing but LE. Now we are connecting between natural coordinates and local coordinates, that is dou V by dou zeta, it can also be expressed as dou V by dou x into dou x by dou zeta. Here dou zeta by dou x, here it is dou x by dou zeta, this value is substituted here. Dou zeta by dou x, it is 2 by LE. So dou x by dou zeta, it is LE by 2. Okay, this value it is substituted, dou x by dou zeta, it is taken from here. Okay, how it is obtained from differentiating this equation. This is the relationship between the natural coordinates and the local coordinates or the global coordinates or Cartesian coordinates. Next, here the displacement at any point, this is a displacement expression. It is given as h1 v1 plus, see here I have written something different here. It is in terms of dou v by dou zeta. It is in terms of natural coordinate dou v by dou zeta. Here it is dou v by dou zeta. It is in terms of local coordinate dou v by dou x, or the global coordinates dou v by dou x. Dou v by dou zeta equal to dou v by dou x into Le by 2. Here I have substituted this value dou v by dou zeta equal to dou v by dou x into Le by 2. Okay, same thing here, dou v by dou x, Le by 2. Dou v by dou zeta is Le by 2 and dou v by dou x. It is substituted here. It is in terms of natural coordinates, it is in terms of local, global or Cartesian coordinate. Okay, so in short it can be written as displacement equal to Hermite shape functions into displacement. What is Hermite shape function? h1, h2, h3 and h4. h1, h2, h3, h4. And what are q? Q are the nodal displacements at node 1, node 2. That is vertical displacement and slope at node 1 and node 2. So by referring this equation, what can be h written here? Q, it is the nodal displacement v1, and this dou v by dou x, it is the slope v2, and dou v by dou x. So what is the Hermite shape function can be written here? Along with this v1 there is h1, it is written here. Along with dou v by dou x, what is the coefficient of dou v by dou x here? h2 Le by 2, Le by 2 h2. What is the coefficient of v2? It is h3. Coefficient of h4, it is Le by 2. So it is expressed in this fashion. So what are the h and q values? Dou v by dou x, it is the slope. It is in terms of local or global coordinates. It can be written as theta 1 and same thing theta 2. Now the boundary conditions. We know that the element, this is a beam element. At node 1 there are two displacements, vertical displacement and slope. In the vertical displacement, so let us take vertical displacement, that is v1 is equal to 0. This is related about h1 and dou h. It is the first boundary condition. This one related about vertical displacement at node 1. Okay, there is slope. Okay, so at zeta equal to -1 there is vertical displacement and there is no slope. And similarly there is one more displacement here, dou v by dou x or dou v by dou zeta. Okay, that is second boundary condition. This concern this about second boundary condition. There is slope here, so other elements are 0, 0. Zeta equal to -1, there is a slope, so it is 1. Similarly here vertical displacement v2 it is node 2, so zeta is equal to +1 here. Vertical displacement, it is vertical displacement and slope. There is vertical displacement. Okay, actually this should be 1, 0, this is 1 because it is a vertical displacement. v2 it is a vertical displacement at node 3. This is wrong, 0 and it is 1, and there is no slope in the third boundary condition. It is 0, 0. Okay, you make it this 1 and it is 0. Similarly fourth nodal displacement, that is the slope. So 0, 0, 0, it is 1 because at node 2 there is slope. At node 2, that is at node 2, this is the slope. Okay, dou h by dou zeta, that is equal to 1. Okay, so it is about first nodal displacement, second nodal displacement, third nodal displacement, fourth nodal displacement. This is about vertical displacement at node 1, slope at node 1, vertical displacement at node 2 and slope at node 2. Okay, thank you. We will continue in the next video session.